All right, everybody, get ready because today we're doing a deep dive into blockchain.
Yeah.
And I know you want to really get it. We're going to get beyond the buzzwords. We're going to get to those aha moments.
Absolutely. And we're going to dive into some of the source material that you provided us, Blockchain-Basics, which does a great job of kind of breaking it down.
Yeah, and we're going to break it down even further and really bring in those real-world connections so that this stuff really sticks. So to kick things off, imagine, trying to throw a surprise party, but there's a twist.
Okay.
Instead of one person coordinating everything, everyone has to plan it independently and secretly.
Okay.
No central organizer allowed.
Right. So that's distributed. When you think about it, that's a good analogy for a distributed system, which is what blockchain is built upon. So it's a very different way of thinking about information and control. Instead of that central, like when you do a Google search, that's very centralized. This is very different.
Yeah, it's like instead of like Google's the authority on everything, it's like this, like a giant collaborative party planning committee.
Right.
Spread across the internet, and no one's really in charge.
And no one's in charge.
Yeah.
And that's where some of the beauty comes in, but also some of the challenges, right? Because just like with your surprise party example, you have, you have advantages. You're resistant to censorship. You have great privacy, but you also have problems that come along with that.
Yeah.
With that distributed system.
Yeah, and that brings us to the fascinating world of pirate ships.
Pirate ships.
Yes, you heard me right. The source material uses this really creative analogy to explain a complex problem known as the Byzantine Generals Problem. And trust me, it'll make sense in a minute.
It's a classic problem in computer science, and it really boils down to this idea of how do you achieve consensus, agreement when you don't know who to trust.
Right. You may have a bad actor in the mix.
You may have a bad actor.
Yeah.
Just like in your surprise party, you may have that one friend that can't keep a secret.
Oh, yeah.
To save their life.
Right.
Right.
Exactly. Okay, so picture this. A pirate ship under siege, surrounded by 6 army ships. To sink the scurdy dogs, the army ships have to attack at the exact same time.
Coordination.
Total coordination. But here's the catch. One of the captains is a traitor, secretly working with the pirates.
Oh, no.
Talk about some drama.
And this is where that analogy is so great, because what they talk about is, if you think about traditional communication, if you pass a message, kind of linearly from one ship to the next,
yeah,
that can be exploited, right?
But like whispering the party details around the circle.
Yeah, exactly.
Things can get lost or, misconstrued along the way.
And so they highlight that that's a losing strategy because, that traitor can manipulate the message. They could send different messages to different ships.
Right.
And so that's where the source material kind of brings up this winning strategy, which is how do you overcome that?
Okay. I'm all ears.
So they have 2 rules with this winning strategy. The first one is they build in a time delay. So when a captain wants to kind of relay that message, hey, it's time to attack at this time, they have to wait 10 minutes before they can relay that message to another captain. And the reason for that is it makes it much, much harder for that traitor to fabricate messages from multiple captains. They're racing against the clock, essentially.
Right. Like you can't just say the cake is ready, you got to bake it. You need that time.
Exactly. And then the second rule, which I think is even more important, is that each message must include all the previous messages received. So it creates this chain.
Okay.
So I get a message. Not only am I going to relay that message after 10 minutes, but I'm also going to include all the previous messages that I've received as well. And that's kind of like a lie detector, because if one of those messages is wrong or has been tampered with,
yeah, you can see it.
It's going to break the chain.
Right.
So it's a brilliant, kind of solution. And this is essentially a simplified way to understand this concept of a hash chain, which is how, blockchains actually work.
Right, where each message is like a block and they're all kind of chained together.
Exactly. Each block contains this unique fingerprint called a hash that links it to the previous block. And that's what ensures this data integrity. So that's what they're talking about with this pirate ship analogy.
So we've got this distributed system, and we've kind of tackled that trust issue.
Right.
Everyone's literally on the same page, even if there's some bad actors lurking about.
But the complexities of distributed systems don't end there, right?
Right.
We also have to think about what's called the CAP theorem. And the CAP theorem highlights some of the trade-offs when you're designing these systems.
Yeah, and they actually illustrate that through a really relatable story in the source material about this guy named Kaushik who's, trying to run this online business. And they call it happyspouse.com.
Happy Spouse. Yeah, I love that example.
Right.
So happyspouse.com, right? They are in the business of helping people remember those important dates, anniversaries, birthdays, you name it.
Yeah.
And so Kaushik, he's running this business, and, at first, it's just him and a notebook, right?
Keeping track of it all.
But then the business starts to grow, and he realizes he needs some help, so he brings his wife on board to help answer calls.
Smart move. Now they've got like a 2-person distributed system going.
They're distributed, right? They each have their own notebook, and they're providing that availability. Someone's always there to answer the phone. But here's where the CAP theorem comes in. So they've got the availability down, but now they have to think about consistency, right? Because what happens if a customer calls Kaushik and says, hey, I need you to remember this date, and he jots it down in his notebook?
Yeah.
But then they call back later, and they get his wife on the phone, and she's got different information in her notebook.
Oh, that's a recipe for disaster.
Yeah.
An angry spouse is the last thing that Kaushik needs.
Right. And that's the problem with these distributed systems. You can end up with these different versions of the truth, right?
Right.
Just like with those messages in the pirate ship example, if they're getting tampered with or changed along the way.
So how do they try to keep things consistent? Are they like constantly comparing notes?
Yeah. So at first, that's exactly what they do. They're like, okay, we got to make sure we're on the same page. So they're syncing their notebooks, like religiously, right? They're prioritizing that consistency, making sure they have the same information. But then life happens, right?
Uh-oh.
They have a disagreement. Communication breaks down. And suddenly, they can't even agree on what day it is, let alone manage these appointments.
Yikes.
Right. So now, they've lost that partition tolerance. Their system can't handle that breakdown in communication.
So it's like they can have the consistency or they can have the availability, but it seems like they can't have both. Not without that, like, rock-solid communication.
Exactly. It's a trade-off. And that's what the CAP theorem is all about. You can only pick two.
So if you're designing a system, you have to choose which of those are most important. Which two would you prioritize?
It's a tough choice. And in the world of blockchain, you see different blockchains making different choices, right? Depending on what their priorities are.
So it's about finding the right balance for what you're trying to achieve. It seems like for something like Bitcoin, you wouldn't want a system where your money could just disappear because of a network glitch.
Exactly. So Bitcoin prioritizes consistency and partition tolerance over availability. They want to make sure that once a transaction is recorded on that blockchain, it's there to stay, even if the system might be a little bit slower at times.
Okay, that makes sense. So we've got these distributed systems, we've got the CAP theorem, and this idea of how blockchain solves that whole trust issue. But I want to circle back to this hashing thing. It sounds so mysterious.
It's really not that complicated. We hear about hashing a lot with security, like keeping your passwords safe online. But in blockchain, hashing is all about ensuring data integrity. It's like creating a unique digital fingerprint for a piece of information.
Okay.
And even the tiniest change to that information, like if you change one word in a sentence.
It's going to completely change the hash.
Exactly.
Yeah.
Like a totally different fingerprint.
So it's like if you change one ingredient in a cake recipe, you end up with a totally different dessert.
Precisely. And here's the thing. Just like you can't look at a cake and know exactly what ingredients went into it, you can't reverse engineer a hash to get the original data.
Yeah.
It's a one-way street.
Interesting. So you can go from the data to the hash, but you can't go from the hash back to the data.
Yeah.
Okay. So how does that work with, like, tons of data? Blockchains are dealing with, tons and tons of transactions. It seems like it would get really difficult to manage.
And that's where this cool concept of a Merkle tree comes in. Imagine a family tree, but instead of listing relatives, each branch contains the hash of the data below it.
Okay, so you have this like interconnected web of hashes all kind of like stemming from this one single point.
Yes, exactly. And that point at the top is called the Merkle root. It's basically a digital fingerprint for that entire set of data below it.
Wow. The source material actually had a helpful diagram for this.
Yeah, figures 1.3 and 1.4, I think it was.
Right. But can you give me an example? Like, how would I use this in real life?
Sure. Let's say you buy, a rare vintage comic book online, right? And you want to prove to your friend that you own it, that digital copy. With a Merkle tree, you don't have to show them your entire transaction history, which could be huge.
Right. Who wants to do that?
Instead, you just give them a few hashes that link your purchase to the Merkle root of the blockchain. It's like leaving a trail of breadcrumbs that leads straight to your purchase.
And if anyone tries to tamper with any of that data, it would change that Merkle root and everyone would know.
Exactly. It's incredibly secure.
So we've got a pretty good grasp on the basics now. Are we ready to jump into some specific types of blockchains?
Let's do it. We've talked about the foundation, but now let's look at how it actually works in practice.
Perfect. Most people have heard of Bitcoin, but what exactly is a Bitcoin blockchain?
In the simplest terms, it's a giant public ledger. Imagine a digital notebook that keeps track of every single Bitcoin transaction ever made. Every time someone sends or receives Bitcoin, it gets recorded in this notebook.
So if I'm sending Bitcoin to a friend, it's not like I'm attaching it to an email or something like that?
Nope, not at all. You're broadcasting that transaction to the entire Bitcoin network.
The whole network?
Yep, and it gets validated by a bunch of computers called miners. Then it's added to a block, which also contains a bunch of other transactions. That block is linked to the previous block, and boom, you've got a blockchain.
It's all connected. That makes sense. What about Ethereum? That's another big one. How is that different from Bitcoin?
Great question. Bitcoin is primarily used to record transactions, right? Ethereum, on the other hand, is like this decentralized computer that can run applications. We call these applications smart contracts.
Okay, so instead of just recording that, I sent you some Bitcoin.
Ethereum could actually record the execution of a contract, like an agreement that says every time your favorite sports team wins a game, I automatically pay you a small amount of Bitcoin.
That's cool. So you're automating that agreement through code.
Exactly. And every single step in that code's execution, every change, every decision, it's all recorded on the Ethereum blockchain. It's like this public record of everything that happened.
So Ethereum is taking that transparency to a whole new level. Doesn't that create a ton of data? Recording every little detail must take up a lot of space.
You're right. That's one of the big challenges they're trying to address. Storing the complete history of everything can get out of hand quickly. But developers are coming up with clever solutions to address that.
I can imagine. But before we go too far down that rabbit hole, I wanted to touch on something the source material called out the trader's perspective.
Ah, yes. It's easy to get lost in the technical stuff, but we can't forget that blockchain is also about, money, or at least value exchange.
Right. People are trading cryptocurrencies like Bitcoin and Ethereum every day.
Exactly.
So how does it actually work from a trader's point of view? How is it different from trading, stocks or bonds?
Well, at their core, cryptocurrencies are still currencies, right? They need to function as a medium of exchange, a store of value, and a unit of account.
Okay, so I can buy a pizza with Bitcoin, hope it goes up in value, and I can tell you exactly how much that Bitcoin is worth in dollars or euros.
Yes, exactly. And what makes cryptocurrencies unique is that they operate in this decentralized way. There's no central bank or government controlling them.
Right.
And that's where blockchain comes in. It provides that underlying framework for trust and transparency, making sure that every transaction is secure and verifiable.
Okay, so we've zoomed out to the big picture of what blockchain does. But now I kind of want to zoom back in. What does it actually look like up close? What would if I could peek inside a Bitcoin block? It's like we're popping the hood on this thing.
Yeah, exactly.
We've heard all the terms, but what's actually under the hood?
So in the case of a Bitcoin block, what we're talking about is this package of information, kind of like I guess you could think about it like a digital container.
Okay.
And just like a container has specific sections for different types of cargo, a Bitcoin block has this defined structure.
Okay.
And actually, the source material, figure 1.8, shows a nice diagram of this.
Cool.
But essentially, the most important part of that is the block header, which is kind of like the control panel of the block.
Okay.
And this header contains a bunch of crucial information about the block. It includes things like a timestamp, when the block was created, a version number, so what version of the software was used. And then here's the really important part. It includes the hash of the previous block.
So each block is carrying this little record of the one before it.
Exactly.
Okay.
Exactly.
Bro.
That is what creates that chain.
It all comes together.
That is what makes it so secure.
Yeah.
Because if you were to try to tamper with a block,
yeah,
you wouldn't just be changing that one block. You'd have to change every single block that came after it as well.
It's like trying to rewrite history, but in a digital format.
Exactly.
Yeah.
And it becomes virtually impossible to do that at scale.
Yeah.
Now, remember those Merkle trees we were talking about earlier?
Oh, yes.
The block header also includes that Merkle root, which is remember that digital fingerprint for all those transactions?
Wait, okay.
So it's like a summary of everything that's happened.
Gotcha. Okay, so we've got this, nice, well-organized block. It's ready to join the party. It wants to be a part of this chain. How does it actually get added? This is where the miners come in, right?
The miners, yes, this is where they shine.
Mm-hmm.
So mining is the process of adding new blocks to the blockchain.
Mm.
And you can think about it almost like a giant global puzzle competition.
Okay.
And all these miners around the world are racing to solve this puzzle.
And what's the prize?
Bitcoin.
Okay.
So the first miner to crack the code, they get to add the next block to the blockchain.
Mm.
And they are rewarded with some newly created Bitcoin.
Oh, very cool. What's the puzzle and how do they solve it?
So it all comes down to finding this special number, which is called a nonce.
A nonce.
And what the miners do is they take all that information in the block header, a hash of the previous block, all that stuff, and they combine it with different nonces. And they keep hashing it over and over and over again.
So they're just trying a bunch of combinations until they get the right one.
Yeah, it's like a brute force kind of thing. They keep trying until they find a nonce that when you hash it with a block header, it results in a hash value that meets certain criteria. The network kind of sets these criteria. It's almost like trying to fit a key into a lock, and only one key is going to work.
Okay, that makes sense. Now, the source material mentioned something about like a 10-minute target. What's that about?
Ah, yes. So to keep things kind of stable and prevent blocks from being added too quickly or too slowly, the Bitcoin network has this built-in mechanism that adjusts the difficulty of the puzzle.
Oh, okay.
So if the miners are solving it too quickly, they make it harder.
Oh, wow.
Like changing the locks on the door, essentially.
Gotcha.
And if it's taking too long, they make it a little easier.
Okay.
And this ensures that, on average, a new block is added to the blockchain roughly every 10 minutes.
Wow. Very cool. Very, very cool. All right, so we've covered mining. There's one more term that I wanted to ask you about. Forking.
Forking, yes.
It sounds kind of intense, like the blockchain is splitting in two.
Yeah. And in essence, it kind of is, but it's not always a bad thing. You can almost think about it like, software updates.
Okay.
Sometimes the community wants to make changes to the way the blockchain works, maybe improve security, add new features, things like that.
Right.
And so if that change is what we call backward compatible, meaning, the old versions of the software can still understand and work with it, it's called a soft fork. It's like adding a new feature to your phone, but it doesn't break any of the old features.
Right.
But then sometimes you need to make more significant changes that require a whole new version of the software, and that's when you get a hard fork. And that essentially creates a permanent split in the blockchain, resulting in two separate chains, each following their own set of rules. And that's where you get into these big debates and discussions in these communities, because it really is, which path do we want to take?
It's like a fork in the road.
Exactly.
But there's no going back once you've chosen a path.
That's a great way to put it. And we've actually seen this happen in the real world. Like with Ethereum, there was the ETC split. It was a pretty big deal.
So a hard fork is like this fundamental disagreement within the community about the future direction of a blockchain.
Exactly. And it really speaks to that decentralized nature of it, that no one person or entity can just dictate the rules. It's really up to the community to come to some sort of consensus, and that's not always easy.
Yeah. Definitely not always easy. Well, we've gone from the basic building blocks of a blockchain all the way to these like big picture questions about, the future of this technology. And I really appreciate you breaking it all down and making it easy to understand.
Of course, happy to do it. Blockchain is a constantly evolving field, and there's so much potential to revolutionize tons of different aspects of our digital world.
Absolutely. To our listeners, thank you so much for going on this deep dive with us into the world of blockchain.
Yes, thanks for listening, everyone.
We hope you learned something new. Until next time.